Hello, in this video I'd like to talk about a proof by contraposition and first tell you how it works and then demonstrate one such proof. So first in our proof, we want to prove that P implies Q. The contrapositive statement, which is logically equivalent to this, would be not Q implies not P. If we manage to prove that not Q implies not P, we have also proven P implies Q because the two statements are logically equivalent. Why are they logically equivalent? Well, let's make a Venn diagram. Let's say this circle represents Q, and we have P within it. Thus, let's look at our original statement. P implies Q. If P, then Q. Well, looking at P, if we're inside of P here, then we're also definitely inside of Q, just because P is inside Q. Thus, P implies Q. Now, looking at not Q implies not P. Well, if we're not inside of Q in the first place, then we can't be inside of P. In this Venn diagram, let me just make a box around it. The box would be the universal set, everything outside. And if we're not inside Q, there's no way we can be within P. Thus, the two statements are logically equivalent. Moving on to a contrapositive proof that will demonstrate this fact. So let's say, let's prove the lemma that we've shown in class. Supposing n is any integer, we want to prove that if n cubed is a multiple of 5, then so is n itself. Well, for a proof by contraposition, we first want to write down the original statement, which would be, for all n element of integers, that if 5 divides n cubed, this means that n cubed is a multiple of 5, then 5 also divides n. Now we want to write out the contrapositive statement. For all n element of z integers, notice how the quantifier remains the same. Then 5 does not divide n, then 5 also does not divide n cubed. This is the statement we want to prove. Supposing our assumption not 5 divides n holds, then 5 should also not divide n cubed. Thus, for our first statement, we want to prove contrapositive statement. For all n elements of integers, that if 5 does not divide n, then 5 also does not divide n cubed. Having this been our given, we can make the following definitions. There exists a k element of integers, and there also exists an r element of 1, 2, 3, 4, such that n is equal to 5k plus r. This can be, this is by the definition of Euclidean division or the quotient remainder theorem. Why does this hold? Well, in our statement we assume that 5 does not divide n. If 5 does not divide n, then there must be a remainder when 5 divides n of 1, 2, 3, or 4. The remainder cannot be 0 because that just means 5 divides n in the first place. And the remainder can also not be 5 because 5 can just be put back into the k, and then the remainder will then again be 0. Having done this, we can plug this in and solve for n cubed. So by 2 and algebra, n cubed will be equivalent to 5k plus r cubed. Well, after doing some algebra, which I will skip the steps up to save some time, we get that n cubed is equal to 5 times 25k cubed plus 15k squared r plus 3k r squared plus r cubed. Notice how I've taken out a 5 here, and I have a remainder left here of r. The original n cubed fully expanded would look like something like this. 125k cubed plus 50k squared r plus 5 kr squared plus 25k squared r plus 10kr squared plus r cubed. We can take a 5 out of this big expression here and have a remainder of r cubed on the side. Now there are multiple ways to do this and continue solving the problem, all of which are correct, but I'll just do by mods. Well, but first, let's set 25k cubed plus 15k squared r plus 3kr squared equal to some m element of integers under closure of integers under addition and multiplication. Thus, from 4 we can get that n cubed is equivalent to 5 times n plus r cubed. Notice how this looks familiar to our original statement where we set n equal to 5k plus r. This time it's just 5m plus r cubed, and it's again very similar to the quotient remainder theorem. We want to prove that r cubed is not equivalent to 0. We can do that by a couple of steps. So n cubed mod 5 is congruent to 5m mod 5 plus r cubed mod 5 by mod rules. Developing this, we can say that n cubed mod 5 is equivalent to 0 mod 5 plus r cubed mod 5. Why is this? Because there's already a 5 here, and mod 5, the mod 5 of anything that is a multiple of 5 is just 0. Therefore, we know that n cubed mod 5 will simply be equivalent to r cubed mod 5. If we prove that r cubed mod 5 is not equivalent to 0, then we can show that n cubed mod 5 is not equivalent to 0, and thus 5 does not divide n cubed, making n cubed not a multiple of 5. We can do this by cases. We've previously defined R as 1, 2, 3, or 4. Thus, we have 4 cases where R is 1, 2, 3, or 4 respectively. So, case 1, R is equivalent to 1. Thus, R cubed mod 5 would be equivalent to 1 cubed mod 5, which is just equivalent to 1 mod 5. 1 mod 5 is not equivalent to 0 mod 5, and thus that's the first case proven. Well, case 2, R is equal to 2. R cubed mod 5 would be equivalent to 2 cubed mod 5, which becomes 8 mod 5, which is equivalent to 3 mod 5, also not equivalent to 0 mod 5. We run through these cases one by one. Case 3, R is equal to 3, so R cubed will be equivalent to 3 cubed mod 5, which becomes 27 mod 5, which is equivalent to 2 mod 5, also not equivalent to 0 mod 5. Last case, case 4, R is equal to 4, R cubed mod 5 is equivalent to 4 cubed mod 5, which is equivalent to 64 mod 5, which is equivalent to 4 mod 5, also not equivalent to 0 mod 5. So running through all possible cases and doing this by exhaustion shows us that there is no case where R cubed mod 5 is equivalent to 0 mod 5. Thus, since r cubed mod 5 has been shown to not be equivalent to 0 mod 5 by step 7, then it also means that n cubed mod 5 is also not equivalent to 0 mod 5 by 6, step 6. Remember, we equated n cubed mod 5 to r cubed mod 5. Thus, since they are both not equivalent to 0 mod 5, there is no way that n cubed could be divisible by 5. Since n cubed mod 5 is not equivalent to 0 mod 5, then n cubed is not divisible by 5 according to mod rules. Having proven the contrapositive, we have also thus proven the full proof. So we end the proof here. And that's an example of a proof by contraposition. Contraposition, to give a brief overview, is very similar to a direct proof. In fact, it is a direct proof once you've gotten the contraposition. You first write out the original statement, you find the contrapositive statement of that statement, and then use the and then you prove the contrapositive using a direct proof, which should not be any different from proving the original statement with the direct proof. Other than that, it's just proving the contrapositive. Once you've done that, since the two statements are logically equivalent, you've also proven the original statement. And that is a proof of the lemma using mods and cases and also contraposition.